Hello everybody. Today we are going to continue with our discussion on design of adders. So let's first summarize what we have done in previous lecture. In previous lecture, top of it we have seen how to design an n-bit adder using ripple carry technique as well as a faster design using carry look ahead adder. So this was done at top level, but on a side perspective, we have also observed during the previous lecture that how Boolean equations were formed. We have seen to create Boolean equations, we have created truth table, and secondly, we have analyzed the circuit and we have created Boolean expression based on the functionality, whatever we have observed. We have also created Boolean expression using the recursive technique where we were replacing one particular variable with the other variable. So these are the various methods that we would be generating Boolean equations so that we can design a Boolean logic or a Boolean system. So this is one question which have been carrying forward from last many lectures, that how do we create input for a Boolean for a digital logic. So these Boolean equations essentially came from the functionality or the behavior. So in previous lecture we have also seen that there could be many variables in one particular expression. So for example, in 4-bit CLA, we have seen that to generate Cout of 4-bit CLA, this carry look ahead expression contains 9 variables: P0, P1, P2, P3, G0, G1, G2, G3 and input carry. So 9 variables if it was a 4-bit CLA. If the number of it instead of a 4-bit CLA, if it would have been 18-bit 16-bit CLA, the number of variables in this expression would have been 33. So yes, so this point also signifies that yes, number of variables in a particular expression could be very, very large. And this also reinforces one point, that if number of variables are very, very large, this our method which we have studied previously, like Kuhn-Minkowski or K-map, will not be very, very sufficient. So that's why when we studied these particular expressions, when we did these expressions, we put no effort in minimizing, although they were not minimizable also. That's a side effect, but a side point. But yes, we put from our side also, we have not put any effort to minimize, to use K-maps or Kuhn-Minkowski method, because if we had used, then it would have taken exponential amount of time. The other thing which we have also learned from previous lecture is, yes, there is a trade-off between area and delay. So we have seen that if a ripple carry adder is very small in area, but if we keep on adding more areas, so for example, if we use carry look ahead adder, the delay would minimize. And to further minimize the delay, we can use 2-level CLA or multiple level CLA. So with multiple level of carry look ahead, carry generation unit area would keep on increasing, but time will also reduce to certain extent. So this trade-off also tells us that yes, if we are willing to put in more area, there would be some chances that delay could be reduced. We can't infinitely reduce the delay, but yes, to certain extent delay can be reduced if we keep on adding some area or some technique which is a little more complex, but they can help us in reducing area. So because this addition is very important topic, and it's a very fundamental thing for any digital system, for any kind of a processing system. So that's why in last 50-60 years there has been huge amount of research in creating very fast addition circuits. So other than this carry look ahead adders or ripple carry, they are the basic fundamental techniques. But using those techniques, so in CLA, in carry look ahead, what we have seen that carry can be generated parallelly by looking ahead. So basically we can have a carry for some individual blocks, and then we can use the other blocks carry to finally generate the final carry. So all these combinations are certain kind of we call it parallel prefix adder. So why parallel? Because now carry is being generated parallelly, so it's called parallel prefix adders. So there are various combinations people have thought of and people have created. So some of the popular ones are Brent Kung, Lander Fisher, or Cogstone. Ling adders are also sort of parallel prefix adders. So these parallel prefix adders are some variation of carry look ahead, but in a more general sense, where the combination how this carry would be generated in a look ahead manner would be slightly different in each of them, and they would have one advantage or the other advantage over the others. So other than that, there are also many other type of fast adders which have evolved during last half a century. Carry select adders, carry skip adders, carry save adders, and we can also create hybrid of all of them. So let's say we can use for 4-bit we use CLA, and for rest of them we use carry select adder or carry skip adder. So all those combinations are also there. So in this lecture we are not going to talk about all different all these options, but we will focus on these two special ones, carry select adders and carry save adders. So why we are selecting these two? This carry select adder will be using some different functionality, and that functionality, that type of optimization, we can think of applying somewhere else also if it is required. So the idea is to know what kind of digital techniques or digital optimizations we can apply given certain circumstances. And carry save adder is a fast adder, not for two operands, but for a very special case. But it's important to know that particular scenario. So let's first understand what carry select adder is. This carry select adder, the idea is that the problem there is that we don't know in any particular adder, we don't know what would be the carry in, and because we don't know carry in, that is the major problem, and because of that we can't compute what would be the carry out. So what carry select adder do, that instead of knowing what would be the carry value, it assumes, it compute the sum. So here it computes the sum assuming that carry is 0. So this is a k bit adder where A is also k size, B is also of k size, and some 0 is produced based assuming that input carry is 0, and similarly C out 0 is produced, and it also compute the hardware is duplicated, so it will create two different instances of k bit adder. One which will take 0 as a carry in, another which will take 1 as a carry in, and so it will also produce, that's why some 0 as well as some 1. Some 0 means when carry was 0, C out 0 means when carry was 0, similarly some 1 when carry was 1, and C out 1 when carry is 1. So we have to note that this is completely a replicated circuit, so area is simply doubled, but not the delay of both of them would be same. Now why do we do computation, this duplicate computation? Because at the end what we can do is, as soon as we know when this C in is there, then we can see that okay, based on C in, if C in is 0, then it will select some 0. If C in is 1, then it will select 1. Similarly, it will also do the similar mux thing here. If C in is 0, then it will take C out as C out 0 as the C out, and if C in is 1, then it will take C out 1 as the output. So the idea is that by the time this computation is done, C in would be available. So this way, this multiplexing can help us. So we can go ahead in computing the addition, and in parallel there could be other adder which would be doing its work so that it can generate C in, and when C in is generated, then we can create the output and see that which one to be selected. So when this C in to be generated, when this C in to be given, for that let's do a quick delay analysis. So delay of, let's say, which k bit adder, let's say we take the simplest one, a ripple carry adder. So if we take ripple carry adder as a input, so as the implementation of this k bit adder, the delay of k bit adder we understand in a ripple carry is 2k delta g. Delta g is the gate delay, so gate delay into 2 into k, that would be the delay of k bit adder. Now to get the output, there would be a delay of mux also. So this mux will consume 2 delta g delay. So the final delay is going to be, for k bit adder, it's going to be 2k delta g plus 2 delta g. Now we have to ensure that this C in is available. The C in is available at least at this 2k delta g time. Okay, so if C in has to be available at 2k delta g time, so that means that the adder which is preceding this adder, so basically this is computing some k bits, the adder which is doing from where the C in is being computed, that should generate the C in, or C in as C in by the time this particular sum is available. So that should also take 2k plus 2k delta g time. And from this equation, it seems that, let's say, that particular adder is also using this carry select adder combination. So that means that should be k minus 1 bit adder. Okay, so now so that means we are creating sort of groups. So one group which is using k bit adder, the another group which is using k minus 1 bit adder, so on and so forth. So this delay is selected in such a way that the delay when sum is there is equal for all the groups. So if I have an n bit number, so first highest order k bits I'll use for this carry select, k bit carry select, and then the lower significant bits I can have k minus 1 bit carry select adder, and then k minus 2 bit carry select adder. So this looks like arithmetic progression. So that means I can create a arithmetic progression, and I create groups in such a way. And the overall thing, what I am ensuring that at a particular group, so for example at this, the sum as well as the C in from the previous group is computed at the same time. Similarly, sum at this particular group as well as carry in from the previous group are computed at the same time. So that's why it forms sort of an arithmetic progression. Okay, so if it is arithmetic progression, it also means that let's say if the total addition is for n bit, the largest k value would be equal to, or the largest value would be equal to ceiling of under root n. So let's say if n is 32, so that means the maximum value of k is going to be 6. So the total delay, maximum delay, will also depend on the largest value of k. That means 2 under root square n plus 2 would be the delay of this carry select adder. Now if n equal to 32, these are going to be the groups. So we have to start with 1, 1, then 2, then 3, then 4, then 5, then 6, then 7, and whatever remaining would be given to 3. Would be given and would be the last group. So this way, this particular type of adders, although it looks little orthodox, that we are doing computation twice, but it seems to be very effective, because by the time we are doing computation, some other guy is calculating, and whatever was our depending thing, so we were here dependent on C in. So this C in can be computed in parallel, and we are duplicating the hardware and doing it twice. So this is a very general optimization technique which can be used in designs. So basically in designs as well as in coding algorithms or wherever. So the idea is that if we are able to do two copies, like, and then finally choose that which one should we select, it can reduce the delay, but it is increasing our effort of design. It is also increasing the amount of area or cost also. Okay, but delay can be minimized. So let's take a very example from our assignment. So we don't know what kind of assignment professor is going to give, but we know that either he will give this assignment or that assignment. So we know the two options which he will give. So what we can do is we can parallelly work on both the options. As soon as professor will give the assignment, we can give him the answer. So this, and similarly in other many scenarios wherever we don't know what our dependency is going to be, we can be prepared, but this be preparation can help only if the number of options are finite. So here the number of options were only 2, so either carry in could be 0, carry in could be 1. So if it is 2 or finite number of options, then we can still think of doing it in parallel, but if the it's not so, then we don't know. So this is also called speculation in some cases. Speculation means that we speculatively assume that if the output is going to be 0, then we can do this, and if output is going to be 1, then we can do this particular processing, and then when we came to know what is the output, based on that we can select our final output. Okay, so this was using unequal groups, but with equal groups also this particular algorithm is equally effective. Let's quickly see how equal groups carry select adder can be created. So let's say we create two adders of like we divide the, let's say we are designing a 32-bit adder, we divide into two parts, 16-bit adder and 16-bit adder. So first 16-bit adder is a standard one, and we don't know how it is inside implemented. So whether it is CLA, whether it is carry select adder or carry skip adder or parallel prefix adder, we don't know. But let's assume that it is a 16-bit adder. The other one we are implementing, we are designing and implementing it using carry select adder. So that means there are two combinations of this 16-bit adder. One which is taking 0 as carry in, the other which is taking 1 as a carry in. The upper significant bits, upper 16 significant bits of the B is part of input here. Similarly, upper 16 bits of A are part of this input here, and we are adding both of them. We are getting sum 0, we are also getting sum. So when this C in would be available, the C would be available only when this particular addition would finish. So this addition is the lower 16 bits of A and lower 16 bits of B. So as the C out would be available, that would be given as a C into this particular adder, and then we can decide what would be the sum, whether it is sum 0 or whether it is sum 1. Now if we see that whether this would be advantageous or not, it is certainly advantageous, because the delay of this particular 32-bit adder, what is the delay of this 32-bit adder is whatever is the delay of 16-bit adder plus delay of this mux. So the addition, this 16-bit addition and this 16-bit addition can be done in same amount of time. So this sum and this sum would be produced in same time, but here an additional mux delay would be required. So the total time would be delay of 16-bit adder plus 2 delta G. So using this carry select adder, we are able to reduce the delay to half, approximately half. Now can we do it better? Yes. So this inside implementation of 16-bit adder is not defined here, so we can do the way we want. So in previous combination, when we were having unequal groups, we we thought of using only ripple carry adder because the size of each group was non-uniform. So one of the group was 7, then 6, then 5, then 4, then 3. So if the size of group is variable, then using some other effective adder like carry look ahead adder or carry parallel prefix adders will create some sort of a confusion. We are not sure when the delay would be, what delay would actually match the two parts. But here, if we are using carry select adders with equal size of groups of equal sizes, then lot of optimizations are possible. So one optimization is certainly this, that we can make sure that this 16-bit adder is a fast adder. The other possibility is that this particular technique of carry select adder we can hierarchically apply. So we can design this 16-bit adder again using carry select adder of 8-bit and 8-bit. And then again 8-bit carry select adder we can design using 4-bit carry select and 4-bit carry select. And the leaf level 4-bit carry select 4-bit adder we can implement using carry look ahead adder. So the only thing we have to ensure here that the two parts which we are implementing should have same delays to have the optimized results. So this way, this carry select adder can also lead to an overall delay of order of log n. Why order of log n? Because we can break them into 2 and then break them into 2 and then break them into 2. It is actually order of log n. It's not equal to log n, because this 2 delta g delay would be there in every iteration. So for example, when we are creating this 16-bit adder using a carry select adder, then it would be a delay of 8-bit adder plus again 2 delta g. Okay, so still the order would be equal to order of log n. It's a very effective technique, and it's a very generic thing also, which can be applied to different kind of circuits.